Hello and welcome back to Calculus 1 Saturday edition, section 5.2 on definite integrals. Last time we talked about integration in general. We talked about what we call indefinite integrals, where we solve the integral and we get a function on the other end, which is the antiderivative. We put plus c at the end. And then we had a section on area under the curve where we use rectangles to approximate area under the curve. So that was all done to intro into today, which is going to be one of your very important lectures, where we learn definite integral, the one that will be used in every application in STEM and so on you're going to have after today. Now, this definite integral needs to be introduced, it needs to be derived. So let's see first what we need here. We talked about area under the curve. We talked about having a function of some kind split into these rectangles, and the rectangles don't have to be the same width. They can literally be any width. It's easier when you have them the same, but they don't have to be the same. And each one of these rectangles is going to create, if you take, let's say, right-hand approximation, each one of these rectangles is going to create a rectangle to its left, and you can compute the area, approximate the area, in this case AR, by multiplying f of x1, which is the height, times x1 minus x0. Now, as you can see, I can't use delta x because each one is different. So I have to go and compute all of them separately. And I need to have 5 of these. So what I'm doing here is always the height times the width. And that gives me the area of that particular rectangle. And I continue with this method throughout the calculation. There we go. And I have 5 calculations, right, to come up with 5 rectangles. And then when I add them all, I will have the approximate area. Now, there is error, right? We talked about it last time. There is error. All of this stuff here is error. And clearly, for this particular question, the actual area is bigger than what we calculated. Oops. Because, right, there is this error. Now, we also said last time that if you want to do better, what you need to do is to increase the number of rectangles. And the more rectangles you have, less error. And we can see that right on the picture, because a lot of error will be eliminated by having more rectangles. So now we can simplify this picture by saying, you know what, let me have a lot of these, but I'm also going to evenly space them because I want to be lazy, right? And then there will be a delta x, which would be the same everywhere. And I can calculate that delta x when I say b minus a divided by the number of rectangles I have. So this was the formula which we wrote down last time to compute this delta x, because delta x is easy to compute when you have the interval and you have the number of rectangles. So we had the interval, I believe last time was 7 minus 3 was 4, and then I did 4 rectangles, so delta x was 1. Now this allows us to approximate the area, let's say area from the right side, approximate, with the formula that says delta x times, and then you just have your f of x1 plus f of x2 plus f of x3 plus dot 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 plus f of xn as the last one. And then we said, you know what, we can actually write this in with that summation notation, because that was much easier, less writing. Delta x summation I goes from 1 to n of f of xi, right? So this was our short notation for it. So we had two important formulas last time. We had this formula here and this formula here. Now, you can't compute using this formula, because this is just a formula to condense a lot of writing. You have to write it in the exploded form, what I call the exploded form, right? Because you need to plug in all of these functions computed at different numbers, x1, x2, x3, and so on. So as much as this formula here is useful to us to shorten the notation and make it look intimidating so we can go around and annoy others, right? It's completely useless for calculation, because I can't compute anything, because right, each one of these values, x1, x2, x3, right, they're all different numbers, and I can't plug all of them at the same time in one f of xi. I have to separately compute each number. So it's a cool, right, notation, as I said, to shorten our writing, to keep us, be lazy. It's excellent tattoo, for instance, right, to annoy others. It's also good for that, right? If you're gonna go to any of these Thanksgiving protests that are scheduled for next week, right, you can use this throughout the protest to annoy others. Anyway, is there a way to make this better? And the answer is yes, right? In life, you can always make things better or worse. And in this case, we can have a better version of this, more precise version of this, if we keep increasing n. So if I keep stuffing in more and more and more of these rectangles under the curve, the more rectangles I stuff in, the better my calculation will be. There will be less error, because right, when I draw my rectangles on this one, you see that these very tiny errors in comparison to what you had in a picture above. So more rectangles, less error. That is the rule. Now what you also see is that more rectangles means that this delta x becomes thinner and thinner and thinner. So if I am to go with this method of making these rectangles thinner and thinner and thinner, all the way through, I got bored, you can see that error is disappearing, because pretty much every single one of these on top is kind of flat and matches the curve pretty much perfectly. It's not perfect, still going to be error. Now, what if I am able to fit somehow infinite number of these rectangles? Now you might go say, whoa, you have a finite interval a to b, you can't stuff infinite in between. Yes, I can. How many numbers do you have between 0 and 1? And your answer better be infinitely many. Because if it's not, we can play a game for a very long time. Now, no one picked up this game because everyone understands immediately, right, when I give an example. But if you want to pick up the game, let's go. I pick 0.5, and then you say, oh, 0.51, and then I say 0.511, and then you say 0.5111, and we can keep going like this, emailing back and forth forever. I mean, not forever, until we expire, right? But the thing is that in between any two numbers, whole numbers, decimal fractions, I don't care, between any two numbers that are not the same number, you can write infinitely many numbers in between them, right? Right. So, you do have infinity on the finite interval between a and b. So, if I am to squeeze in here infinitely many rectangles, they become infinitely thin. Okay, well, that's a concept now. I have a rectangle of width near 0. That's something to think about, which a lot of people can't wrap their head around. But as soon as I write that delta x is equal to b minus a over n, and then say that b minus a is some kind of number divided by infinity, oh, that does go to 0. Because I remember now that the limit when denominator is going to 0, right? We remember L'Hopital rule. We remember 2.5 section from chapter 2 all the way back, when you had like a problem that said limit 3 over x, and as x goes to infinity, was it going to 0? Because I said if you take 3 pieces of paper and you cut them infinite many times, you get 0 on the other end. That's exactly what is happening up there. As n goes to infinity, the entire delta x is going to go to 0. So when you get infinite number of rectangles stuffed under the line, each width of the rectangle is going to go to 0. So we can stuff infinitely many rectangles. Now another thing immediately pops out. Okay, if I have a finite amount of rectangles, I'm always generating some error. But if I have infinitely many of them, then they all align up under those infinitely many points. And since practically there is no width to them, there is no room to make error. Ooh, we just found the exact area. All I need to do is to fit infinitely many rectangles. If I am able to fit infinitely many, infinitely thin rectangles, I have exact area. Oh, let's build that. Let's build that. So, if I take one representative rectangle with the width of delta x, and these points on the side being xi and xi plus 1, let's say, and you are computing a function f of xi for the height, and this is my, what you would refer to in your future calculus courses as representative rectangle. We'll give it a name dx later. So if you look at your representative rectangle, this is what I can do. I can say, well, this representative rectangle here is simply f of xi times delta x. So this is one rectangle, representative. So the area of one rectangle is height times the width. Yeah, that's your elementary school math, right? You know how to find area of the rectangle. Nothing new there, nothing special there. But then you say, okay, professor was talking about adding many rectangles in. Maybe 4, maybe 10, maybe 17, maybe 137 if you like pain, right? So let me put many rectangles in. Oh, okay. So now this is many rectangles, meaning more than one. Okay, so if I have one rectangle calculation, which is what I know how to calculate because it's length times width, in this case height times width, it's fine. And then I'm going to say, well, how about I compute another 10? So, so I have 11, let's say. Okay, so that's going to be, put the summation and put that n up there to be 11, and you're good to go, right? You have 11 rectangles. That was last class. Now, in this class, I said, and you know what we can do? We can make them infinitely many, actually. So all I'm going to do is I'm going to send this n to infinity, because as soon as I send n to infinity, we see what happens. This becomes infinitely many rectangles to add up, and this becomes infinitely thin, sorry. And all of that together, all of this together becomes exact area. Now the question is, do we know how to compute this, right, for area under a curve? So, with the limit, infinitely many rectangles. Whoa! What? So that's all we need to do? We start building at one rectangle, then we add many rectangles by placing the sum in front, and then we just put that limit where we say, well, let the number of rectangles go to infinity. Wow! As soon as I write this down, I have exact area, right? No error anymore, because the rectangles are infinitely thin. They fit under each point in the interval, right? Which is, right, the function is consistent of infinitely many points. That's what the function is, that line. Now, computer science is going to understand this very easily. Oh yeah, I have, 100 pixels, and I just need to light up those 100 pixels. And when they light up, right, they create what we perceive as a continuous line. Okay, you can think about 100 pixels on a screen lining up like that and creating a continuous line, but this is infinitely many points lining up like that in a reality of a function, right? It's infinitely many points lining up like that to create a function. And now under each one of those infinitely many points, I'm going to stuff infinitely thin rectangle, and there is no room for error because these infinitely thin rectangles have no width to them to create error. The reason why these rectangles are creating errors is because they're fat, right? And then their left side and the right side are under two different heights, and it creates either undershoot the area or overshoot the area because they're fat, right? But the infinitely thin rectangles, right, are collapsing the left point and the right point into the same point, which means there is no thickness to create that physical area which creates error, right? So what we just did is we created a formula that will give us, right? We created a formula that will give us the um, exact area. Now there is a name for this. It's named after a German mathematician who came up with this stuff in 1800s, and that mathematician is called Riemann. So this is something that is called a Riemann sum, and it's written down as a formula, and we can use it to compute area under the curve. So here it is, Riemann sum, and it is limit n goes to infinity of the summation I goes from 1 to n of f of xi times delta x. There we go. So use it to compute exact area under the curve f of x. All right, so now that we know this awesome formula, maybe we should take a look into how to compute one of these. And yeah, this is where the fun begins, so lock the doors. No one is leaving, right? So what do we do here? Well, you know what? Let's do something simple that we can kind of verify geometrically. And then let's go and do something, I guess, more interesting. So let's say that you want to compute area of the triangle with a height of 5 and the length of 4. So you can calculate area easily as 1/2 4 times 5, which is 10. Now, obviously, why simple if we can complicate things? So let's go ahead and have our fun with the Riemann sum formula. See, this line here has the equation of y equals, and the slope is negative 5 over 4 x plus 5 as y-intercept. We just create a linear line there, right? The slope is 5 up and 4 over, but it's actually 5 down because the line drops. So negative 5 over 4x. Okay, I just got my function, right? My function is f of x is equal to negative 5/4 x plus 5. Perfect. I have that. And then I need the rest of the stuff. So limit n goes to infinity, summation I from 1 to n on f of xi times delta x. All right. So I can compute delta x immediately. We see that our interval is 0 to 4, right? Because you are looking for area under this triangle right here. And the interval is, right, the entire rectangle left to right. The most left and the most right points are 0 and 4. So that's easy, right? We got that one. So delta x is b minus a over n, which means 4 minus 0 over n, and that's 4 over n. It's 4 over n because we have n rectangles, and remember we are sending a number of rectangles n to infinity, so we are not having 10 rectangles to say 4 over 10 or anything like that. We have infinitely many rectangles, so I'm just going to call it 4 over n. Now, are they infinitely thin? Sure they are. 4 divided by infinity, right? The next piece of the puzzle here is this xi, because I have to express each one right in my division, 0 to 4. I'm going to have infinitely many of these divisions. And when I look at one of these, right, is xi. So how do I express this xi in terms of everything else? Well, it's going to be a plus I delta x. If you think about it, let's space it out. This is your a, where you start. This is your x1. This is your x2. This is your x3 and x4, going on, blah, 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 to meet b someplace. You see that each one of these is delta x width. We know that delta x is 4 over n for us, but so to get to x1, I need to start at a and add the delta x. To get to x2, I start at a and I add 2 delta x's, right? Because x2 is right here, and I need to add 2 delta x's to get to that one. x3 is a plus 3 delta x's. Oh, okay, well, I have a counter, 1, 2, 3, 4, 5. Well, that's labeled as I. And then delta x everywhere, whatever delta x is in our case, 4 over n. So my a is 0 plus I 4 over n, which works out to be 4i over n. So I have my xi. Not to be confused with complex numbers I, right? This I is a counter, not a complex number. So be very, very careful about that. We do not use complex numbers in calculus. Right, this is basic calculus. So we're going to now move to figuring out f of xi, and that should be simple because we have negative 5 quarters times xi, which is 4i over n, and then plus 5. That simplifies into negative 5i over n plus 5 when you put all of that stuff together. All right, we are ready. Limit n goes to infinity, summation I goes from 1 to n of negative 5i over n plus 5, everything times delta x, and delta x is 4 over n. So this over here is your xi, and this over here is your delta x. So all I did is I just used the formula, right? We know what the formula is, and I just plugged in all of the stuff that I found. Well, I needed xi to make f of xi, so I'm plugging in this and this into the formula, and there you go. So all we need to do is to compute this mess and get that 10. We better get 10, otherwise we broke calculus, and there's no reason to learn anything else, right? So now the only thing I can do is distribute. So we start with the limit n goes to infinity, summation I goes from 1 to n, and over here I have negative 20i over n plus 20 over n. Oh, n squared, oops, on the first one. N squared on the first one, because n times n is n squared. Now, the property of the sum, it's just a sum, which means it can be distributed for each one of these independently, because it's just a sum. It's simple distributive rule. I goes from 1 to n. Wait, is it distributive rule or associative rule? So if you have summation of, let's say, 2i plus 4, and then you distributed 2i plus summation of, I'm just trying something here to see, when you do this, right, when you put each one to get its own sum, this is a sum, then technically what you did is over here you had, well, let's call this xi, better, xi. So you have 2x1 plus 4, 2x2 plus 4, blah, blah, blah. And over here you have 2x1. Yeah, it's distributive property. Okay, cool. I just wanted to check. Anyway, so each one gets its own sum. Each one gets its own sum. And now, when you look at this, the variable that the sum operates on is I, not n, I. So you can kick constants and other parameters like n in front of the sum because the sum doesn't care about those. Now we had that rule for limits, we had that rule for derivatives, we have that rule for integrals as well. So you have them for sum as well, right? So you can kick out negative 20 over n squared and just have sum of I, plus you kick out 20 over n, you have sum of 1. Now, if you go to your textbook on page 243 or 345, hold on, 345, you will find formulas that compute this for you. And those formulas will give you this. So negative 20 over n squared, and the formula for I becomes n plus 1 over 2 plus 20 over n becomes just n. Now, as I said, these formulas take this whole sum and write it as this, takes this sum and writes it like that, and that's on page 345. You will find that in your textbook. From this point on, the problem is a joke, right? Basic chapter 2 limit. You have your n cancels, 20 and 2 cancels to negative 10. So you got your negative 10 n plus 1 divided by n plus 20. And when you send n to infinity over here, n divided by n is 1. You got your negative 10 plus 20. You got your 10. Woohoo! So we were able to find, and please learn this, not because you need it, just because if you are some kind of STEM major, at least once in your life, area of the triangle will come up. And imagine if you do this instead of the formula. It's the ultimate troll move, okay? When I say, what was the area of the triangle? Bring up the chair and 2 pages of paper, right? Look at this. To come up with the exact area under the curve, actually the area of the triangle. This is what you can do with Calc1. Absolutely amazing, right? Area of the triangle, the most interesting way to compute, right? And this is when they say, you know what, once you learn enough calculus, you don't have to remember a lot of the formulas. Yeah, well, now look at this. You can forget your formula for area of the triangle, right? Isn't that cool? I hope it is. All right, let's take a look.
So when we have kids, this is what we need to teach them before they go into algebra?
Yeah, this would be amazing. Like you know, the kid comes up and says, Daddy, what was the area of the triangle? The teacher was talking about it. Bring the chair up. Bring the chair up. Let me show you uh, the most fun way to compute something that you can be that you can do in like 10 seconds. Here's a 30-minute solution to the same thing. That's how we did it in old age. Before, obviously not, right? Greeks were talking about the area of the triangle 2,000 years before Riemann came up with this calculation. But you know, come on, right? If you want to be a troll, right? This is what you learn. And trust me, there is nothing better than leaving behind, you know, this. And let's say on a diner, you know how they have those usually those big papers with all of those commercials on that they use like a place setting or something. Yeah, the back page is empty. And I think I said enough. Every time I go anywhere, I just leave something obscure, like the old Calc 3 with a triple integral or something like that. You know, it's just fun, right? So you can use this, right, at your disposal. I know I opened the door, and now it's yours to learn it well enough so that the troll is successful. And I use it every time when someone wants to be a wise you know what with me and say, what do you know, you blah blah blah. Okay, look at this. And then you come up with this stuff, right? And they can't even pronounce it. So it's good, right? It's good to get annoying people out of the way. It's good to troll. It's good to, right? It's not useful for calculation because you've seen that there is a formula, right, to calculate. However, the next question of f of x equals 2x cubed minus 6x plus 3 cannot be computed by the triangle method because there is no formula, right? We have the formula for square and rectangle and circle and trapezoid and kite and parallelogram, right? Those are the areas that we can compute using those formulas, right, 2,000 years ago. But now this 2x cubed, you can't even graph this in peace, right? You have to suffer and bleed, right, through that section on graphing and those first and second derivative tests and all other horrors, right, to graph this one by hand if you don't have the calculator. And then what you're going to find? You're going to find the curve. And when you find the curve, you still go, well, I can approximate with 6 rectangles, right? You're not going to have exact area because there's no formula for it in geometry. And your approximation is not going to give you exact number. Even if you go in your code, if you code it, and I did tell you to code the area under the rectangle, it's just a joke of a loop, right? Even if you code it and you go there and you put 100,000 rectangles, it's still approximation. It's not exact. So, right, let's talk to Mr. Riemann, ask him and his formula for help to come up with this. So I have this 2x cubed minus 6x plus 3, and let's put that on some interval, let's say 3 to 7. It doesn't really matter what you pick. You can pick any interval, don't care. All right. So what is the area under the curve? But exact area under the curve, not approximated one. Okay, so delta x is equal to 7 minus 3 over n. It's again 4. How about we change this to 2, so it's not 4 every problem. So 7 minus 2 is 5 over n. Okay, there we go, 5 over n. Now our xi is a plus I delta x. It's like that's like a formula which calculates our xi's. So that's 2 plus I 5 over n, which is 2 plus 5i over n. And now we need to stick that one in here and in here to come up with our f of xi, because we need that one for our limit formula. Okay, we can do that. It's 2 times 2 plus 5i over n cubed, we're going to cry there, 6, 5i over n, and then plus 3. Hello, algebra. 2 cubed is 8. Plus, those of you who don't know, the coefficients are 1, 3, 3, 1. So it's 3 times 4 times 5. So 3 times 4 is 12. 12 times 5 is 60. I over n. Plus, now the coefficient is again 3. So 3 times 2 is 6 times 5 is, oh, but 5 is squared. Now 5 is squared. So that's 50 times 3, 150. I squared over n squared. Plus 125 I cubed over n cubed. If you have no clue what I just did, is I expanded this one in one shot instead of multiplying it 3 times. If you don't know the expansions of binomials and all of those kind of things, then go ahead and multiply it on a side 3 times. I know the expansion, so I don't have to go through those horrors of multiplying everything forever. So this is now 16 plus 120 I over n plus 300 I squared over n squared plus 250 I cubed over n cubed minus 30 I over n plus 3, which is equal to 19 plus 90i over n when I combine like terms, plus 300i squared over n squared plus 250i cubed over n cubed. Bring this up during your Thanksgiving dinner. It is a lot of fun for the whole family. All right. There it is. I got my f of xi. So the area is limit n goes to infinity, summation I goes from 1 to n. Here is my 19 plus 90i over n plus 300i squared over n squared plus 250i cubed over n cubed, all of that times 5 over n, which is my delta x. So this puppy over here is your xi, this puppy over here is your delta x, and you have your problem set up, right? So you can distribute 5 over n, give summation to each one of them, use the formulas from the book to compute sums, and then take the limit, you're done. Yeah, it's very structured, right? When you get a hang of it, it becomes a joke. Like, it's more annoying to write it out than to actually do it, but again, it takes time to get there. 19 times 5, that's 95 over n, right? I hope, because 5 times 10 is 50, and 5 times 9 is 45. 50 plus 45 is 95. Or, smarter way to compute, 20 times 5 is 100. but you have 19 fives, not 20 fives, so you overshot by 1 5. So you subtract a 5 from 100 and get 95. Okay, plus 450i over n squared plus 1500i squared over n cubed plus 25 times 5 is 75, and then there is a 0. No, those are lies. Those are lies. 4 of these, so 1, 2, 5, and a 0. There we go. I cubed over n cubed. So think about this, is you have $250, but you have 5 piles of $250. So 4 piles of $250 will make $1,000, and then you have one other pile of $250, right, which is the 5th pile. So 1250. All right, cool. So now, once we distributed this delta x to each term, now it's time for each one of these to get its own sum. So we are separating these now. You're getting your summation. I goes from 1 to n of 95 over n plus another summation. For 450 I over n squared, I goes from 1 to n plus another summation. I goes from 1 to n for 1500 I squared over n cubed. And finally, the last one is summation I goes also from 1 to n of 1250 I cubed over n. This is supposed to be to the 4th, because when I multiply n in, supposed to be n to the 4th, right? When I multiply n times n cubed is n to the 4th. There we go. So now we have to kick out all of the constants. So from the first one, I'm kicking out 95 over n. That has no i's, left with 1 inside. Plus 450 over n squared gets kicked out, and you are left only with the I inside. Now, I hope you see, guys, sum of 1 and sum of I. Sum of 1 and sum of I. You will always have sum of 1, sum of I squared, sum of I cubed, and those are your formulas on page 345. Yep, always the same. It gets really repetitive and boring after like problem number 3. Once you figure out what you're supposed to do, it's just like, I gotta write it out. So kick out again constant, you're left with I squared, and finally kick out the constant. Oops, hit shift, there we go. 1250 over n4, boom, 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 I1, 2, and I cubed. All right, it's time for our page to get all of those summations out of the picture to compute them. So you get 95 over n times n. That's this one. Then you go to plus 450 over n squared times n plus 1 over 2. That's that one. Plus 1500 over n cubed, and then for I squared you have n plus 1, 2n plus 1 over 6. That's your I squared. And finally, plus 1250 over n to the 4th, and you have n squared, n plus 1 squared over 4. So these formulas, again, are on page 345. Limit n goes to infinity. 95 plus 450 n plus 1 over 2n. There's still more things to simplify. Come on, tablet, don't do that now. Plus 1500 times n plus 1, 2n plus 1, divided by this 1n cancelled, 6n squared, plus 1250 n plus 1 squared over 4n squared. I cancelled 2 of the n's. over there. Now, for those of you that earned PhD in limits in chapter 2, there is a difference between passing the test and knowing. The student who knows will just be able to tell the limit by looking at this without any calculations. Because you know that when the powers are the same, for limits that are going to infinity, when powers are the same, you just get to write front coefficients. Well, do we have the same powers? Hell yes. N and n. N times 2n is 2n squared, and there is n squared on the bottom. And then n squared again, and n squared again. We do have the same powers everywhere. So I can just write front coefficients. 95 plus 450 over 2. I don't need the limit anymore, actually. I'm done with the limit. 95 plus 450 over 2 plus 3000 over 6, because there is a 2 over here, so 2 times 1500, and plus 1250 over 4. That's it. We got it. So compute this. Well, we have 595 when I combine these two terms, and then I have plus 450 over 2 plus, when I cut this in half, because I want the denominator to be 2, so I can add it. When I cut it in half, I get 625. And now when I add those two, I get 1075 over 2. Now that's not perfectly divisible, but it's, you know, it's good enough because it's just 0.5, so who cares? 595 plus 537.5. There we go. So when you add this, you get 11, a 3, a 2.5. I hope that's good. That's exact area. Units squared. Whether it's inches squared, miles squared, whatever the hell squared. It's something squared. It's right. It could be centimeters, millimeters, whatever. Another good Thanksgiving talking point, right? So think about it. Think about it. Cool. So now that we successfully induced panic in 120% of the students, we don't need this calculation at all. The same way we don't need the limit calculation for the derivative, because you spent the entire chapter 3 learning shortcuts. That derivative of sine is cosine, derivative of ln is 1 over x, and stuff like that. You spent entire chapter 3 learning the shortcuts, so you don't have to do that limit. Well, you already learned the shortcut for this. It's called the integral, the antiderivative. So you get to bypass all of this with a simple integral of 2x cubed minus 6x plus 3 dx. Is that what it was? Minus 6x. Yeah, minus 6x plus 3. And now the new thing is we have to write 2 and 7 on the integral sign. And you go, well, I know how to compute integral. I studied 4.9. I'm getting tested on it today, right? So I know how to solve this. And you're saying we can skip all of this? Yeah, that's exactly what I'm saying. What's the derivative, the integral? It's 2x to the 4 over 4 minus 6x squared over 2 plus 3x. And here's the new one. We don't put plus c. We put this line and say computed at 7 and 2. That's new. We're going to talk about it. That's why we have 5 too. So this becomes x to the 4 over 2 minus 3x squared plus 3x computed from 2 to 7. And the way you compute this is you go and you say f of 7 and f of 2. So that's going to be f of 7 minus f of 2. Oh, well, that's easy. That's 7 to the 4th over 2 minus 3 times 7 squared plus 3 times 7. That's my f of 7 minus f of 2. Okay, 2 to the 4th over 2 minus 3 times 2 squared plus 3 times 2. At this point, everyone's like, where's my calculator? Yeah, the entire process of what we did replaced by these two lines. All of this, all of this, all of this replaced by these two lines. Woohoo! I don't hear a lot of cheering on the other side. If you don't think this is absolutely amazing and insane, and you have no emotion, and that's sociopathic behavior. All right.
Yay!
There we go. There we go. One finally. Thank you. Thank you. So now we are going to compute these things, like 7 raised to the 4. Yeah, that's 2000 and there we go, divided by 2 minus 3 times 49. That we can do that. It's 147 plus 21 minus 8 plus 12 minus 6. When you distribute this negative, don't forget to distribute the negative. Like that's where your grade dies, when you mess up these signs because you didn't distribute minus, arithmetic. Like you do the calculus, you're able to integrate and you do all of these things, and then you don't distribute the minus sign, and it's wrong answer, and your bridge collapses and 150 people die because you didn't distribute the minus sign. Like, yeah, welcome to civil engineering 101. Distribute that negative, okay? That's enough of that. That's 1200.5, and then minus 126, and that's a 6, and that's a negative 2. So that makes that 8. And then that's 0.5. That's a 2. That's a 7. 11. 1172. Oh, pfft. Yeah, something I didn't calculate something correctly. These two answers have to be the same, obviously. Kill me now. Well, again, I'm going to put my bets rather on calculus here with integrals than the thing up there with. But yeah, I'm actually using calculator now because I'm lazy to check all of this. 147 plus 21. I shouldn't be, but then we live in the time when laziness is. Oh, I just made it worse, actually, with a calculator. Is this good? So 7 to the 4th, yes, divided by 2, yes, minus 3 times 49 plus 21 and then minus 8 and plus 12 and minus 6. 1072.5. Calculator confirms this. Okay, let's check my integration. Copy 2 to the 4 and then over 2, that's good. And then 6x squared over 2, that's at negative 3, that's good. And then plus 3x plus 3x. Yep, everything is good. So that means that my calculations here did not go well. So let me try this again with the calculator this time. 95 plus 450 over 2 plus 500 plus 1250 over 4. I calculated correctly. Oh, so there's going to be a mistake somewhere in constants coming up with this all of this. There's no way in hell I can find that one now. I could look into distribution of this one again because those are the largest chances. So 2 cubed is 8. And then 2 squared is 4 times 3 in a coefficient and times 5. That's 2060. That's good. Then I have to square 5, which gives me 25, and then multiply it by 2 and multiply it by 3. So that's 75 times 2 is 150. That's good. And 5 cubed is 125. That's good. When I FOIL that, that's good. And then times 2, 16, 120, 300, 250. And then I have times negative 30 is there, and then plus 3. Yeah, I have no clue now where the mistake is, but there is a mistake in numbers, in coefficients here somewhere, because these two answers have to be the same, and I need to get 1072.5. This is correct because integration obviously is much less calculations, and that one should be correct. This is not good. Let's go and do the triangle one. So we had integral 0 to 4. We had negative 5 over 4x plus 5 dx. So this has to come out the same as the one, and we have to get 10 when we do this, right? We have to get 10. So we integrate, we copy the constant, make this x squared over 2 plus 5x computed from 0 to 4. So this is our integral. So we did the basic antiderivative where x became x squared. And now it's negative 5x squared over 8 plus 5x computed from 0 to 4. Now we plug in 4 first. That's negative 5 times 4 squared over 8 plus 5 times 4. And then we subtract. When you plug in 0, it's just going to be 2 big fat zeros, right? Because 0 times whatever is 0. So that's not going to contribute. Now, guys, don't always say, oh, 0 doesn't contribute, because e to the 0 is 1 and cosine of 0 is 1. So if you have e's and cosines around, you are going to have values. So don't disregard 0 immediately, right? And in some other cases as well, like if you have, let's say, 3 over x squared plus 1, well, that's not going to be 0, right? Because 0 plus 1 is 1, so this is 3 when x is 0. So be very careful about statements. Oh, right, it works for polynomials. It works for sine and tangent, but it doesn't work for e and cosine and some of these rational functions and so on. Anyway, that's negative 5 times 16 over 8 plus 20, which is negative 10 plus 20 and we get 10. So here is your way to find area of the triangle given area of the triangle, right? Given this calculation for the integral. So we saw, right, we got 10 now. I do have some error with one number somewhere didn't go well, and maybe we can go back later and check during the review or something if you're interested. But those two numbers have to be the same, because when you do the Riemann sum, which is exact area, is what we have with a definite integral. So now here is the big formula for 5.2. This is what you are focusing on. This is what you are looking at in 5.2. So limit n goes to infinity of summation I goes from 1 to n of f of xi delta x is equal to the integral a to b of f of x dx, right? Which all give you exact area under curve. So you have a function f of x, you have your a and b, and you can compute with either of the two ways. Now obviously you will pick integral because integral is easy. So there's your formula. And to compute what we call the definite integral, you don't have that plus c. You have integral a to b of f of x dx. You find your antiderivative f of x, but instead of plus c, you are going to put this time around, you are going to put computed from a to b, and that's going to be f of b minus f of a. This integral will follow you through the end of your education, and then beyond, obviously, if you are actually doing serious design work, research work, you can't avoid it. Way too many applications. Your entire chapter 6 and most of other and half of every other chapter of Calc 2 is this integral, right? More than 60%, 65% of your integrals in Calc 2 are definite integrals. Like, if you don't know this, there is no way to score more than 20 for the whole course. Just think about that for Calc 2. Like, this is something that this L'Hopital's rule, basic derivative rules, basic antiderivative with a plus c, which is actually a part of this integral, and then section 5.5 that we are going to cover on December 5th. Like, those are the sections that if you don't know, your Calculus 2 course is impossible. Not improbable, not difficult, just impossible. Okay? So you have to understand that without this formula that you see on the screen right now, there is no Calc 2 in any way, shape, or form. And for me, to prove this is very easy. I just push one of the Calc 2s, and then, I mean, you already see on this page, you already see the definite integral. Now, this one is actually even crazier because, as you can see, one of your limits was infinity to begin with. So that's going to be built up on eventually. But here we go. Go anywhere in here. All of the formulas, 0 to 1. Next section. What are the formulas? 0 to ln 4, right? 0 to 7. What is the next section? Boom. Integral 0 to 6, you can see it. Length of curve, next section. 3 to 8, 0 to 60. Next section, 6, 6. What is the integral? Negative 1/2 to half, for instance. Every single one of these. There is no way in hell you can pass anything. You can't pass the first exam, you can't pass the course if you do not learn these definite integrals and the way to compute them with upper limit minus the lower limit plugged into antiderivative and then go carefully to line up all of your numbers and things. Yeah, Calc 2, forget about it. And I could have gone into every chapter. I just don't want to waste your time with it. I said what I have to say, and then I will leave you to discover that next semester when you go to Calc 2. So about 65% of your course in Calc 2 will be with these integrals with these limits. So you better learn it. Now, what do we have to talk about? Well, when we went through all of that theory and Riemann sums, and then we figured out that we can use this integral, now we can kind of loosen it up and say, what is the integral 3 to 6 4x squared dx, right? Now we can just do joke problems, right? Because why not, right? You can now do anything because you know how to compute this. X cubed over 3 computed from 3 to 6. That's going to be 6 cubed over 3 minus 3 cubed over 3. See, that's your f when you plug in 6, and then f of x when you plug in 3. Now, instead of computing all of this, you go and you say, okay, one of the 6's will cancel at 3, so this is actually 6 times 6 times 2 minus 3 times 3. That's easier to think about that way. So that's 36 times 72 minus 9. Right, which is 63. So it looks like 63. What is the meaning of this? Well, I'm glad you asked, because if you draw your x squared function and you go to 3 and you go to 6, there is area under the curve, and that's what 63 is. There are 63 squares in that area between 3 and 6. So it simply computes area under the curve. There is something that we have to pay attention to, but that's going to be discussed in detail after the break. So we'll come back, we'll take a 10-minute break or something, and then when we come back later, we'll talk about the situations where you have to be careful. How about integral 1 plus e to the negative 2x? Let's just do x over here. Whatever, from 2 to 4. It doesn't matter. We just literally put anything. It doesn't matter. Well, integral of x is integral of 1 is x, plus e to the x stays as is, and then we're computing from 2 to 4. Okay, that's 4 plus e to the 4 minus 2 plus e squared. That's all it is. So that's 4 minus 2 is 2, plus e to the 4 minus e squared. That's exact answer. Can you go get decimals? Yeah, you can. You can punch all of this in a calculator and come up with the approximate answer, right? But like if you were taking this course, let's say at NGIT, this is your full credit answer on a test because calculators are not allowed. So you can't compute any further. But I am going to push this. I'm punching in a calculator right now just to see what we get, and it's 49.21. And I put the squiggle equal, right, because it's approximation. Integral of cosine x dx from pi over 6 to pi over 3. Well, that's going to be a very interesting answer. Integral of cosine is negative sine. No, integral of cosine is positive sine between pi over 6, and pi over 3. This is your A, which is the left, and then the top is B, which is why you always write the bottom first and then the top. And now you have to compute sine pi over 3 minus sine pi over 6, which is root 3 over 2 minus 1/2, which is root 3 over minus 1 over 2. That's it. Done. Very, very quick, very simple. Your job is to plug these values. Now, do you want to compute these things and give approximation? You can. I'm doing it right now. I just want to see what we get. About 0.366. That's, approximation. So computing these integrals is actually easy if you know 4.9, but you better know 4.9 already because it's on the test today, right? So now, instead of putting that plus c, you have these limits. Now, students asked me in the past, like, why no plus c? Well, you actually don't need it, right? If you have, let's say, let's do something very simple, right? 6 to 7, whatever. Let's go 6 to 8, so it's even. So I can divide it by 2 nicely. If I have this, my answer is x squared over 2. Oops, over 2. And then let's say you put plus c and then you go 6 and 8. What's going to happen? Well, when you plug in 8, you get 8 squared over 2 plus c. And then you have minus 6 squared over 2 plus c. Do you see that these c's just cancel because one is positive, one is negative? And they will cancel every time. So there is no point in me writing them ever, because in every single case they will always cancel, because you have f of b minus f of a, and it's always the same, right? That's a formula. You can't change that. So these c's will always cancel, and that's why we don't have to write it, right? So we never write plus c. We just go x over 2, and then what you have? You have 8 times 4 minus 3 times 6. 8 times 4, 32, minus 18. You get 14, and there you have it. Now, is this 14? Guys, we can check that, right? Because if you draw this function carefully, you better have 14 squares. You just have to have enough OCD to draw this properly. 1, 2, 3, 4, 5, 6, whoop, 7, 8. Whoop. I better have 14 squares in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 2 halves. 14. Good. Got it. Right? These things work. I mean, there is no reason for us to verify this, right? It's been proven, and if you take advanced calculus, if you take analysis, if you take, right, you will learn more theory behind this and you will reinforce it, but right, now you can take for granted that, hey, this definite integral computes area under the curve. There's going to be more to it, right? You will have to be careful about a particular thing, but that's next lecture. I don't want to spoil it now. Properties of definite integrals. All right. These are just few formulas. Some of them are quality of life. Some of them are obvious. Some of them are not so obvious. But we need to talk about these. One of the most useful ones that you will be using actually in Calc 2 is the property that you can split integrals on the interval a to b. So if a less than c less than b, then integral a to b of f of x dx is equal to integral a to c f of x dx plus integral c to d, c to b, sorry, b, f of x dx. Now, it doesn't look like much, but it's holy nightmare. This is a good thing. And very easy to understand also. Look, if you have your function f of x right there, and you have your limits a and b, and you want to find this area in between, wouldn't you agree that you can just cut this literally anywhere with c? Anywhere. I don't care where. And just calculate these two separate areas, a to c and c to b, and just add them up. So this entire a to b is this, and then you have this portion there and this portion there. That's all it is. It's very, very simple stuff. So that's that. Another cool thing for these, another cool property, we can call this property number 1, let's say. Property number 2. Integral a to a of f of x dx is equal to 0. Well, that should be common sense, because your width over which you're computing area is 0. Your height is given by f of x, but your distance, right, the thickness is given from a to b. But if it's a to a, there's nothing to compute, because your graph, here's your function f of x, is just this, a. So what is the area, right, under the curve at a? Is 0, because there's no thickness to it. So there's nothing to compute. That's a silly one. We still have to write it. It's silly. And here's another biggie. If you need to swap your limits of integration, you put minus in front of the integral. Now you would say, well, why would I ever need to do this? Well, you will eventually get into 5.5 in Calc 1, and you will discover it very quickly why you would ever need to do this. So just wait until 5.5 and you will know why. But you are going to be doing this, the swap of the limits. Now, it's not too much of a stretch to see why this works. Like, this is one of the very easy proofs that you can ask. I mean, all of these are very easy proofs, right? Over here, you will have f of a minus f of a. Well, duh, that's going to be 0, right, when you solve it. But looking at here, you have f of b minus f of a. And over here, you have negative f of a minus f of b. Well, sure, distribute the negative. When you distribute the negative, they become the same. So the proofs for this are insanely easy, right? You just write out the formula and you compare left and right. But again, it's not a focus of our class. As I said, this is a vanilla Calc 1, meaning we don't do much proofs here or at all, right? It's mostly for that. And there you go. That's it. Now you have those problems that are in the book given, like they say, well, how about integral 1 to 4 of, oops, parenthesis, f of x minus g of x dx, where integral 1 to 6 of f of x dx is 10. Integral 1 to 6 of g of x is 5. G of x dx is 5. Integral 4 to 6 of f of x is 5. Dx is 5. And integral 4 to 6 of g of x dx is 2. So this is what they give you on the right side, and they're asking you to come up with this. Well, draw the lines over here. This is your 1, this is your 4, this is your 6. So you can see from the picture that interval 1 to 4 is actually interval 1 to 6 minus the interval of 4 to 6. Because 1 to 6 has everything, and then you throw away what you don't need, and you are left with interval 1 to 4, which is what you do need. Oh, okay, well, that's easy. So all I need to do is to replace this integral with all of the numbers so that I have 1 over 6s minus 4 over 6s. So this is going to be for f of x. For f of x, I have this one minus that one. So that's 10 minus 5. And then I'm subtracting g, which is 5 minus 2. Awesome. That's 5 minus 3, which is 2. Oh, yeah, just 2. Done deal. We can also, well, we can write it out. Let's see if we can write this out using the rules. So the first rule is that we can go ahead and say that the integral 1 to 4 is actually integral 1 to 6 of f minus g. I'll abbreviate. I'm not going to put of x, just abbreviate. Minus integral 4 to 6 of f minus g dx. Right? So I can do that. That's actually this, the analysis we did. Because this literally means, guys, these divisions, right, which I told you about, that you can have the full area or you can do it in 2 places and add them, right? Well, it works for the subtraction as well. So now this one here can be integral 1 to 6 of f minus integral 1 to 6 of g minus, open parenthesis, integral 4 to 6 of f minus integral 4 to 6 of g. Now, just pick those numbers. F of x dx is 10. There we go. Minus 1 to 6 for g is 5. Minus f 4 to 6 is 5. And minus gives you plus. 4 to 6 for g is 2. So this over here is, well, you can just cancel it and just get 2. There we go. This was problem 55C from homework. So you might run into these types of problems on your homework, right? That's something that is there. All right, let's take 10-minute break. When we come back, 5.3 on fundamental theorem of calculus. Yeah, fundamental theorem of calculus. You don't want to miss that one. So I'll see you soon. I gotta take short break, and then We'll be back for 5-3.